This is the brief on the fundamental role of the Robin condition in defining flow equilibrium. Okay, so what we're looking at are excerpts that compare different boundary constraints, specifically Robin versus Dirichlet. We're seeing how they totally change the final state in systems where you've got stuff being carried by a fluid, that's convection, and also just naturally spreading out, diffusion. The bottom line, the constraint you pick really dictates the entire flow. First, let's talk about the Robin condition. The big takeaway is that it forces zero net transfer of material across the boundary. So, in systems where you have both convection and diffusion happening, this condition makes sure that whatever flows out is perfectly matched by what flows in. It's a perfect balance. But how does it do that? Well, our second point is that the mechanism is dynamic equilibrium. The Robin condition forces the concentration to literally self-adjust right at the boundary. This self-correction ensures the outward push from convection is always perfectly matched by the inward pull from diffusion. It's a constant internal negotiation. And finally, let's compare this to the Dirichlet condition. It's the complete opposite. It acts like a powerful external sink, or a vacuum. By forcing the concentration to a fixed low value at the edge, it creates this massive imbalance. The result? A huge non-zero outward flow, dominated by diffusion as material rushes out. Understanding how boundary conditions enforce either balance or imbalance is just absolutely crucial to accurately predicting long-term material flow.